Hello, good afternoon, and you're welcome to class. First and foremost, like I usually say, the first thing is to give a recap on some of the basic things I feel you should know. Your class rep has spoken with me, and I think we've come to an agreement that your class should, or the test rather, should hold not this week, but the coming week. And I wouldn't be around this week as I expected. Two staff members are having events, and I don't think I'll be able to escape any one of them. So I chose the one that I feel I'm very much more inclined to. So if you're watching this maybe any time from now, which I expect should be Saturday during the class, I will probably be in Anambra State by then. Okay, so basically what I want to do with this set of videos is to first of all do a recap. During the last class we didn't have the projector on, and so I'll be able to do a recap on the previous stuff that we've done, and also be able to continue on the concrete technology like we spoke to. So that way we're able to do something from the last class and do something from also this class also. If possible, if I'm able to do something for the upper next class, I will do and send to your class rep. But for now, I think I'll just focus on recapping the last class, and then let's go into what we have next. All right, so for this class, I will be talking basically on Portland cement and admixtures. And like we said in the last class, Portland cement we'll be treating properties, production, and also uses. Like we said, Portland cement is a major component in concrete. In fact, more or less, there's no concrete in the real sense of it without cement. And like I said in the last class, it was patented in 1824 by Joseph Aspin. And the name Portland, when we say Portland cement, comes from the limestone cliffs in England. That's where that name comes from. Although there are several kinds of cement we have today, but because of that, most cement is always called Portland cement. Basically, cement is the glue or the binder that bonds aggregate together. I'm sure we were talking about aggregates before. Remember our fine aggregate, our coarse aggregate. So in concrete, cement more or less forms, the binder material to hold materials together. Yes, for basic terminology, like I always say, as engineers, we need to get our terminology right. Okay, cement paste is basically a mixture of cement and water, and mortar is a mixture of cement, water, and sand. That's what people use most times for plastering. So what we call plastering, and whatever it's called, is actually mortar. Then the real concrete is a mixture of cement, water, fine and coarse aggregate, which will be sand and gravel in this case. I've dropped a link here in case you need to watch a video on how cement is produced. I wouldn't want to go so long in it. If I can get the video, I'll download and give to your classroom so you can do. Now, a very important thing to note about cement is the fact that the specific gravity is 3.15. I mean, it doesn't matter the kind of cement, it's always 3.15. Due to errors maybe here and there in the lab, you get 3.16. I think once or twice I've gotten 3.17, but it's always usually a 3.15. So it's consistent for all kinds of cement. When it comes to cement, we do not talk so much about the bulk unit weight. Why? Because we spoke about compaction. When you compact, you have a higher weight inside the same volume, which is going to increase the bulk unit weight. So if you loosely compact, if you compact very tightly, you'll be having different bulk unit weight. So we can't really run our calculations that way. Unlike aggregates that you could tamp and all that. You can't begin to tamp cement, and if you want to take it to practical sense on site, how are you going to be sure that the compaction is going to be similar? So most times we do not talk about volume when it concerns cement. We measure by weight, because that's much more accurate for us. Yes, let me just touch the production briefly. Production for Portland cement starts with two main ingredients. First of all, you need a calcareous material, which most likely is going to be calcium oxide. We're talking about limestone, chalk, or maybe oyster shells, things that calcium oxide. You also need an argillaceous material, which will be materials that contain a high amount of silica and aluminum. Clay, for instance, and we're talking about the illite and borylonite, they have an octahedral structure, and one of the important mineral classifications there is silica and aluminum. And so clay could come in, shale, and blast furnace slag if you have maybe iron ore smelting something. So the product of the slag output from such kind of production could also be used in there. Yes, the steps involves first of all crushing the calcareous and the gelaceous material together, grind them together, then you run through a kiln to melt them and to produce what we call a clinker. The clinker is now then mixed with gypsum, and gypsum basically just the setting time. The time is going to take to set the material. General classification, you need to know that cement needs to be kept dry. I think we all know that advert is strong kakaraka like Zumaro, and because the bagging was poor, so air gets inside. If you check the materials, like we talk about 4 different states, and we talked about the SSD states, where we talk about absorption, materials having absorption. Remember, we also talked about some materials having a positive absorption and a negative absorption. Since it's one of the material that has a negative absorption, so it absorbs water. We'll talk more about that. Yes, reactions take place, when you're trying to mix, those materials up. And basically, there are 4 kinds of compounds, that are produced, from the mixing of the materials together. That's still under production. I don't want us to bog. If you want more information, you could go read some more about that. So properties of Portland cement. One of the first properties you need to understand with Portland cement is fineness. It's almost the same thing like talking about particle size, like we talk in aggregates, but because it's the material that most like passes through the 0.045 sieve. So we talk about fineness. When talking about fineness, we're also talking about particle size, but we're talking particle size in terms of also surface area. The amount surface area. Remember, I drew on the board a cube of sugar and granulated sugar. Which one of first will dissolve? We know the granulated one first will dissolve because it has a wider surface area for interaction to occur. So a larger surface area will also cause faster hydration time, in cement. So we're always concerned about how fine the cement is. Usually, the average diameter for cement is usually 0.01 millimeters, and you could just take like I remember specific gravity is 3.15. Yes, hydration. Hydration is one of the major properties of cement. It's a process where it absorbs water, and goes through a chemical reaction that actually causes what we call the binding. So it forms a more solid, a more stable, a more strong, compound that could be used for whatever we want to do. Another structural development in cement paste, like we said, after you add water, it begins to react, and that reaction is usually very alkaline. Within the first 10 minutes, the water becomes highly alkaline, and that's because of the calcium oxide, component of the mixture. And the cement paste will remain workable for around 45 minutes. Remember, we said the amount of gypsum added will affect your workable or the setting time, and that setting time also is more or less like talking about the amount of time you can work the mix before it begins to harden. And usually after 2 or 4 hours, the paste will begin to solidify. You can't work it anymore. All right. So basically, the process involves hydration of the particles, so they can begin to form bonds that will begin to get, like I said. And as long as the water is available and there are unhydrated cement particles, you keep on having hydration reaction occurring. Usually the process rates for the hydration decreases after 28 days. That's why you see most times, like we said in the last class, you always want to take your measurements at 7, 14, 21, and 28. Although, like we said, many people skip the 28 part, which is really not good. Another property of Portland cement is voids. And voids are very important because they either make or mar concrete, depending on what's going on. And the voids in concrete affect the strength properties, durability, permeability, and the volume stability, of your concrete. And different types of voids include interlayer, capillary, trapped voids, and entrained. We'll talk about all these interlayer, capillary voids. You could just take note of them, but majorly for me, the major aspect is the entrapped voids and the entrained air. Now you need to differentiate between both. The entrapped voids are the ones that are caught up, in your mixing when you're trying to mix together, you're trying to get stuff together, and usually it decreases the strength and it creates relatively more permeable pathways, for water to flow. Except you are having, in fact, it's not even good because you cannot really measure the permeability because it's entrapped. When you are working the cement, it becomes entrapped, so it increases permeability, which is always not good. Entrained air on the other side is air bubbles that come up as a result of the hydration reaction. We said there's a lot of oxygen going around and a lot of mixing going on. So there's always a release of some micro bubbles of air. And these micro bubbles, also increase durability. It's just like having sponge. And like I said during the last class, in places where you have maybe a lot of freezing and thawing, you begin to have those micro bubbles being relatively good spaces for expansion and contraction to occur without ultimately damaging the main material itself. Okay. Another property is setting. When we talk about setting, we are referring to stiffening or the change from plastic to solid state. Okay. When we're talking about hardening, it's talking about strength gaining of the cement base. So you should be able to differentiate both. The VCAT penetrating test is used for determining the setting time of cement. And usually you put in cement paste. Remember, cement paste is a mixture of just cement alone and water. So you put inside that bowl and you leave and begin to measure time after the mixturing and everything, and begin to drop the penetrating rod down. At the time when it starts to penetrate 25 millimeter, that's when it begins to set. So you choose that as your initial setting time. And at the time where it can no longer penetrate through, that's the final setting time. So the final setting time is taken as the point when the cement begins to gain strength, or when we talk about hardening. Setting is talking about the process to hardening. If you really understand that, I think that should be very, very clear. Another property is the compressive strength. I'm going to put some material here, but I think it's relatively more straightforward. You get it in the notes. Compressive strength is determined by making relatively small cubes and crushing to determine the strength properties of the material. Another important property, like I said, is the water-cement ratio. Cement, to a very large extent, deals with hydration. Hydration is mixing of water, or the use of water in forming bonds. The unhydrated particles of the cement mixed up with water to begin to form bonds. Okay, so water to cement ratio is very important because it determines whether your mixture is going to be watery, it's going to be workable, unworkable. It also determines setting time, affects strength, because if there is not sufficient water, we talk about cracking or and things like that. And usually the typical water to cement ratio for concrete is between 0.4 to 0.7. So you want to note that. That's an important point. If you have a higher water cement ratio, you need that to cause improved workability. But when the water is too much, it leads to decreased strength, decreased durability, decreased bonding, increased permeability, and increased volume. While it's between wetting and drying. Let's say because of so much water contains this volume, by the time all the water is gone, it shrinks, and you wouldn't want that shrinking ability to occur. There are different kinds of cement. The first one, we said the normal cement, is the one that is used for most general concrete work, and when you don't really need any special properties. It's suitable for floors, reinforced concrete structures, pavements, like they have them. And we also have the moderate sulfate resistant. That's used where you have a lot of maybe attack by sulfates, especially I was talking about construction you want to do in places like shoreline or even rigs, high early strength, that you want to use for quick development of structures. You want something to fast track your construction. Low rate of hydration, if you have a massive structure like that of a dam and you want a uniform setting, you want a low rate of hydration so that everything from top to bottom, from A to B, everything is uniform. You don't want something where one part is hydrating at a faster rate than the other. That will cause relative areas of weakness within a dam. Dam structures are very, very important structures. We don't want to make any mistakes. So we want a cement that has a low hydration, so it's going to take its time to hydrate, to develop strength, and to be more or less monolithic in the structure. You have the high sulfate resistance. It's just more or less like take it from that. All right, so I think I have a better table here. So we have the type 1 normal is the most common type, and it's more or less like 90% of most of the cement that is produced. That's why you don't see most of the other ones, except you really, really need them. Moderate surface resistance 4%, high heavy strength. More and more people are beginning to embrace this. I think Dangote launched a particular brand, talking about the one I said 30 times or something. Like that. So it's basically 5 times. There are other types of Portland cement. You have them in white, type IS, type IP, hydraulic cement, general use, and all that. So we have the list over here. Mixing water. For water used to mix, any potable drinkable water can be used. And if you're going to use water that is not potable, you need to carry out tests for impurities. Remember we talked about alkaline reactivity, so when it comes to aggregates and also it affects cement too, where you begin to see some reactions. You begin to see some reactions, on the wall, more or less like cracks. If you're going to use seawater, can use seawater, but it's usually not advisable when you have reinforced concrete because of the reaction of water and reinforced steel. It begins to swell up. It's expected that at 7 days, any mortar cube, remember we are talking about just cement now, so any mortar cubes you're going to use should have at least achieved 90% of the strength when made with potable water. And whatever you're going to do should not affect what you're going to use, should not affect the setting time. One of the major issues in the use of Portland cement is the issue of wastewater. You see guys after they finish construction, they just wash up and pour the water away. It's not ideal. So because cement the water has very high pH. And when you dump that, it could begin to affect the environment, especially when it seeps down into groundwater, begin to have issues. Those water could be remixed. Could be stored somewhere. Once they settle down, you use the top for whatever construction you want to do, and the bottom over time you could find some relatively good use for it. So I think that's that about Portland cement. I'll produce another video for Admixtures. I believe let's do it in bits, so that way people will be able to get on their phones and stuff like that. So the next class will treat admixtures. Thank you.